So it was the first part of the lab, and we talked about how we could use all of those rules. We had the simulation and we had the lab itself. So at this point, we are going to talk about a very important rule, the Kirchhoff's voltage law. As we guys know, there are two important laws about it. The KCL, which is the very first one, KCL, which says that the accumulation of all of the current that gets inside one node is going to be as the same as all of the current that gets outside of that node. And the KVL, which said that the accumulation of all of the voltages inside a circuit or the closed loop, you can call this mesh or you can call it loop, doesn't matter, is going to be zero. So using these two ways is going to help us in order to somehow see that the numbers that we get from our calculation or our some kind of practical measurement is going to be right or not. So again, what is the objective? The objective is simple. We do have the KCL, the sum of currents entering and leaving a node is zero. It means that either you can say that all of the current that gets in should be as the same as all of the current that gets out, or the accumulation of all of the current is zero. We do have the KVL. It says that the sum of voltage drops and the rises in any closed loop is zero. As you guys remember, the voltage rise means that we are dealing with a source, and the voltage drop means that we are dealing with the resistances. Now you guys see that the polarity. If I assume that the current goes this way, the polarity of source would be negative to positive, while if the current gets inside each of those resistors, the polarity would be positive to negative. So to compare the ideal model with the real world measurement and account for the difference. So we are going to use that to make sure that everything is going to be right. So if your measurement in the KCL and KVL sums are not extremely close to zero, again, as you guys know, we do have something we call as error. Error means that the V of the calculated subtracted by V measured. So most of the time, 99.99% of the time, these two values should be very close to zero, maybe around 5 to 10% more than that, but should be very close to zero. If something happened and these two values are not going to be close to zero, difference of these values is not going to be zero, so we should be suspicious about something, that some part is not right. So this part, if these two guys are not going to be, the subtraction of these two guys is not extremely close to zero, it again is that the tangible problem. The problem could be because of some of these reasons. The wiring is incorrect. Your measurement techniques is flawed. You have some kind of problems. You have ignored the non-ideal effect of your instrument. Again, you have to know that it doesn't matter if you use the current meter or your voltmeter or voltmeter, both of them, they do have some flaws. Flaws means that the internal resistance is still going to have some impact over the whole thing. So here's the test case for the lab number 2. As you can see over here, I do have the 15 volt. So at this point, we do have our circuit. We are going to use it in the second part of the lab. As you can see over here, I do have the 15 volt as my source itself. Then I do have the 1 kilo ohm. I do have another 2 kilo ohm. I do have 330, 5.1K, and I do have the 10K in parallel with all of them. We assume that the direction of the current is this way, which kind of makes sense, right? Because we know the current from the source goes from negative to positive, and it means that the currents I1 is like this, I2 is like this, I3 like that, I4 and I5. So the very first thing that we have to find is about the currents using the calculation. Then we have to do the simulation, and finally we have to do what? We have to use the practical some kind of lab itself to prove everything works. So if you do all of the calculation, by the way, I'm not going to do that right now. I can give you a little bit of hint, but I believe we did enough. You have two ways in order to do that. As you guys remember, we talked about two methods, the nodal analysis or nodal method, and also the KVL method or the mesh analysis. So in the nodal analysis means that I'm going to consider two nodes as my main work, then I'm going to consider the currents that gets in and gets out, which most of the time we assume that all of the currents gets out of this one, and then consider the second one. So I only need to write down some kind of KCLs. It means that, for instance, at this point, if I assume that everything is okay based on that, is I1 equals to I2 plus I3, and at this point I can write down I3 equals I4 plus I5. Or maybe some of you would say that, okay, based on your teaching and your method, you all the time consider the currents like that. Again, that's no problem. As long as you are considering everything consistent, you still can get the right answer. Then we have to write down the KVL we have to write down the Ohm's law for all of them. As you guys know, the current moved through the R1, which is 1K, is going to be the VA subtracted by VB divided by 1K. And also the current moves from D to C is VB subtracted by VC divided by 330. So if you do all of that, at the end of the day, you can find your currents. So your currents, your some kind of the voltages, and obviously after that you can find the currents. By finding the voltages, something around 8.5 and 7.7, you obviously can do all of the calculation to check that whether the answer is right or not. By the way, this answer is right because we are going to prove it using the simulation and also practical thing. So by having all of those voltages, I can find the currents. How I can find the current? As you can see over here, what I want is delta V over R. What does it mean by delta V? Delta V means the subtraction of the negative part from the positive part. VA subtracted by VB. VA is what is directly connected to 15 volt. VB is something that we just found. Subtracted by that, and it would be divided by 1K, so you can find the current. Then for the I2, we can do the same thing. It means that I2 is VB, and so it's going to be VB subtracted by ground divided by 2K. So as you can see, we do have the I2 over here. I3 is VB subtracted by VC divided by 330. By the way, guys, be very careful because at some point we do have the K and at some point we do have the ohms itself. It will be better to convert all of your Ks to ohms in order to not get confused or don't have any problem with the calculation. And then we do have it for I4 goes this way, so it means that the VC subtracted by still ground, this ground there sometimes is not. As I just told you, ground would be better to consider as the node that has the most amount of connections. So as you can see, this part, the big one, has the most amount of connections by itself. 1, 2, 3, and 4, and everything are connected to one node, so we can consider it as a ground. Ground sometimes is there, sometimes is not. Sometimes it's real, sometimes it's hypothetical. We just use it as a reference. As I was just talking about it, I4 is going to be what? Is going to be VC subtracted by 0, subtracted by 0 divided by R4, so we do have this, and I5 is going to be VC subtracted by 0 divided by 10K. So at this point, in order to make your work a little bit simpler, you can somehow combine these two to find the total current. Then you can use the current divider to find R4 and I5, but it would be better to, from the beginning, since the question is specifically asked to find I4 and I5, try not to combine them. So at this point, we can have the sanity check to see that the KCL works or not. Obviously works because we had a base and we had a ground based on the KCL, so everything works. After that, we have to do simulation and obviously practical lab. So at this point, the part of the lab that we did all of the calculations, so we are going to do the simulation at this point. For the previous question, we did the lab, but at this point, I think it would be better to focus on software as well. So as you guys know, based on some kind of the question that we had, we do have the circuit that it has a combination of the series and parallel resistance, and we would like to find a voltage and current for each section. So the first thing that we have to draw obviously would be about the voltage source. So let's go over here. Either, again, you can use the variable voltage at this point, or you can use some kind of the V side. By the way, this is not the right one. Let me just get rid of that and go to the draw. So we do have the input. So we know the two terminal ones. So either we use the AC or DC. So let's go over here and we do have the voltage source, two terminals. So that would be the part. So this guy should be how much? Should be 15 volts, and we don't have any offset, so that's be it. Then we have to add a couple of resistors. So either you can use R on the keyboard and draw that resistor, or if it's hard for you, you can just go over here and add resistor. And another part we do have over here, you can go for draw and add the resistor from this side. You can see you have a resistor, or you can use it from the passive components that you can see that we can just move forward and find the resistor at this point. So then we do have another part. It means that we should connect all of them using a wire and using a ground. So ground comes from this point, or you can just simply put G, and after that you do have the ground itself, or obviously you can find from the draw section. So let's consider this part as this some kind of the ground. Let's put it over here. Then we are going to use R for having our resistors. This is the first resistor. Then we do have another resistor like this. Then we do have another resistor. After that, we do have another resistor. It's gonna be a little bit complicated. We do have another resistor like this, and then the only thing you need to do is just using the wire. So wire is simple. You can just use the wire over here, and then you can just connect all of them side by side. By the way, make sure that when you're using the wire, you shouldn't, for instance, connect this point to this point directly, because on that side, you are going to lose this connection. So do it one step at a time, and also make sure we are going to connect it like this, then connect it like that. Okay, seems that everything is connected because you can see that the current is flowing. Another part that we have to do, obviously, we have to change the values of our resistors. The very first one was 1K. Okay, keep it. The next one was 2K. 2 and K means that, again, it's kilo. Then we do have another one. It is that 330 ohms or 0.33 kilo ohms. Then we do have 5.1K. Then we do have another one, which is the 10K itself. So we do have it. So we do have our circuit. The circuit is completed. Obviously, we need to measure the currents and voltage for each side. So in order to do that, you just have to go to draw part. Then you go have to for the output as labels. And as you can see, we do have the ammeter, and we also do have the voltmeter, right? So in order to find the ammeter, in order to use that one, you just click on that. So we can use the voltmeter for over here. As you know, the voltmeter should be connected in parallel, while the ammeter should be connected in series. We all know about that. So let's go for the outputs and effect. Again, we do this one, we do have the ammeter. Okay, cool. So let's just copy and paste it for each one. The only thing we have to do is disconnect this part, then use the ammeter. Obviously, this is not very good. We have to make it a little bit smaller. Then use the ammeter, connect it like this. Cool. Then we have to get rid of this connection. Again, use the ammeter like this one. Make sure you have the positive on the positive side and negative on the negative side. So you don't have to worry about it that much because the number we're looking for should be each absolute one. But just in case, we are going to make sure that some kind of the number that we are measuring is going to be alongside with the current direction itself. Again, we have to do that. Then for the final one, get rid of that and find this one over here. So everything is okay. We do have all of the currents that we need. As you can see, these currents, the I1, the current that goes through the 1K should be 6.52, which is the right number. And the I2 should be 4.24. You have a 0.23. That's still close. Then we do have the I3 as 2.29, which is 2.28 over here. Then we do have this current, it should be 1.51, yes, and another finally, we should have 0.77 milliamp. Another important part is about the voltages. So for the voltages, at this point, since we are talking about the nodal analysis, we are looking for the voltage of what? Of nodes. It means at this point and this point. So the only thing you have to do is just connect this guy to the positive side. But important thing is that if you want to measure the voltage, you have to consider the difference between this point, or some kind of consider this point, and what? And ground itself. So in order to do that, either we can connect this guy to the ground, or we can just copy and paste another ground to this one. So we do about voltage. As you can see, it is 8 point, zoom a little bit, 8.47, which we had it at 8.48. We have to do the same thing for what? For this side. Again, we are going to do that, and we are going to use the ground to connect it, because we are not going to some kind of have that much of a space. It's not very some kind of beautiful, but it is going to does the job. So we do have a 7.72, and this is what we are looking for. So as you can see over here, we just build up the circuit that we had in our calculation, and we did it over here. It doesn't matter if you use it in a practical. Obviously, in practical, your numbers are going to be a little bit different. Why? Because you don't have anything ideal. Your voltage source, it has some kind of resistor inside. Your wires are not going to be ideal. They are going to lose a little bit of voltage, and also your ammeters and voltmeters are not going to be perfect itself. But still, the difference should be less than 5 to 10%. So, if you guys remember, we were using the voltmeter and ammeter in order to do what? In order to measure the voltage. And as we all know, in order to measure the voltage and current, for the voltmeter should be connected in parallel to our component. It means that we don't have to disconnect anything. That voltmeter is going to be connected in parallel. So the voltmeter is always placed in parallel with the component being the measures, and maintain polarity. So we have to keep the black lead on the less positive terminal to get the positive leading. What does that mean? If I assume that the current goes this way, this is the direction of the current, and I assume that, as we all know, the current goes inside the negative, goes into negative and goes into positive and gets out of the negative, by connecting the red lead and black one like this, I can make sure the voltage that I'm getting would be positive. By the way, it doesn't matter. If you just connect it backward, you would get the negative, but it would be better to know why we do have the positive and why we do have the connection. On another hand, we do have the ammeter. As you guys know, ammeter should be connected. What should be connected? In series. It means that I have to connect the ammeter like this. It should be in the way. Since the resistance inside the ammeter is not that much, it means that that guy is not going to have that much of effect over the whole system. So the ammeter must be placed in series, and you must open the circuit to insert it. This is very important, guys. Be very careful to not connect the ammeter like the voltmeter, because I've seen tons of times that the students do that, but since the fact that the amount of current that ammeter can handle based on the fuse that it has inside of it is very little and so fragile, the fuse is going to blow up. So be very careful about that. So if you connect your ammeter in parallel and it's going to be connected like this, your circuit thinks that you have a short circuit. And since we know current is lazy and most of the time it tries to move through the path that has the least amount of resistor, the short circuit is with the best option. Since you do have a short circuit, based on the Ohm's law, as we all know, I is equal to V divided by R. If R is going to decrease, I is going to increase significantly, and at the end you are going to have the blown fuse and probably blown device. So as we can see over here, be aware the ammeter itself has a small inter resistance, as I just talked about it, so which is slightly change the circuit you are measuring. It means that you are still going to have some problem, not I can say problem, a little bit of error because of the internal resistance of the ammeter, but since it is a small, it's not going to make you that much of the issue. So let's talk about the KVL, our beloved KVL. Again, what does it say? The KVL says that the accumulation of all of the voltages inside one loop or one mesh is going to be zero, and it doesn't matter. As long as you have the closed path, your KVL should be zero. KVL means that the combination of the voltage rise, we do have it because of the voltage source, and the voltage drops because of we do have it for the components, should be zero. And another important fact that we do have is about the power balance. So what does power balance says? Power balance says that the of voltage, amount of power that actually your voltage source is going to produce should be as the same as amount of power consumed by what? By all of those components that you have inside the circuit itself. It means that if I assume that this guy is going to be PSS or PR power source, the PR1, 2, if you add them up, it's PR2 till PR5 should be the same. Or if you add all of them, it should be zero. The amount of power that is going to produce considered as negative, and the amount of power that is going to be consumed is positive. So at this point, you can simply find this some kind of the P power source. Probably we are going to have the simulation related to that. By the way, it's going to be so simple. If you would like to do the calculation better than me by considering those voltage, some kind of nodes, you can write down 2 KCLs, then use the Ohm's law to find all of the voltages. But if you do all of the calculations, your power source is going to be what? Is going to be voltage times current. So it's going to be this amount of milliwatts. So the power dissipated or the power consumed is the accumulation of all of the power that you have inside all of your resistors. So at this point, as you can see, I do have R1, I do have R2, I do R3, I do have this one, and I do have this one. So for finding the power consumed, either I can use this formula. If I do have the current, I can use that, or I can use this formula. Doesn't matter. So if accumulation of all of that, then these guys should be zero, or you can say the accumulation of all of the consumed power should be the same as the power source. As you can see, they're not going to be exact same because of the problem that we do have related to our meters, or maybe because, as you all know, the jumpers or wires, they also do have some resistors, but since it is too small, we don't consider that, or any other kind of errors, we could have a little bit of problem, but that's okay. We can consider that. So what is the important part? The important part is that you have to know the error sources that are some kind of you have to mention in your report, because probably for your work, for your lab report, you have to talk about why you do have the error. So error would be about based on resistor tolerance. As you guys know, the last color of the resistor tries to talk about the tolerance, maybe 1%. Ammeter burden resistors, the amount of resistance that you have inside your ammeter. Yes, it is so small, but still is going to have a little bit effect on your whole measuring. Contact resistors on the breadboard. So obviously in the breadboard and in the jumpers, you do have a couple of resistors inside of that. It's not that much, but if you combine all of these errors together, it could be a little bit considerable. And finally, power supply voltage drop under the load. So we know everything about it. So then, for the lab number 3, we are going to talk about the network theorem, Thévenin and Norton. What was that? If you guys remember, when we were talking about Thévenin and Norton, we talked about the fact that sometimes our circuit is so complicated or complex. So it means that I cannot work with that one because it contains so many series, parallel, or at some point I don't know if it's a series or parallel. So at this case, I'm going to resemble, or I'm going to show the whole circuit these two things: a voltage source in series with a resistance, or a current source in parallel with resistance. So we call this guy as R Thevenin and we call this guy as R Norton, which are going to be the same, but V Thevenin and I Norton is going to be different, but still they're going to have a little bit of relationship. It means that if I look through A, B, or through 2 points, I can mimic the whole circuit by using either the Thevenin model or the Norton model. So what was the objective? Again, we are going to drive and measure the Thévenin and Norton equivalent circuit for a given network as seen from the specific pair of terminals. So the second part would be about the superposition reality check. You don't have to read all of that. I'm going to talk about it. What was the superposition? If you guys remember, the superposition was working for a time that I do have more than one source. For example, VS1 and VS2. And at some point, when you do have more than one source, it would be a little bit complicated for you to do all of the calculation together at the same time. For instance, imagine at this case, instead of R5, I do have another source would be V2. So at some point, it would be a little bit complicated to talk about all of that. It means that it would be better to consider one source at a time. It means that you have to get rid of one of the sources. If it was a voltage source, if you want to get rid of that, your voltage source, for instance, V is going to be 0. Is 0 means that that guy is a short circuit or is going to be considered as wire. So it means that instead of just having your voltage source, you are going to consider a wire. Then we do have another part, and maybe we do have the current source. In order to get rid of the current source, I should be 0. As we all know, I is going to be 0 only for a time then when you do have open circuit. So you have to make it open circuit. At the end, when you find all of the numbers based on the direction of voltage or current, you can add them up or you can subtract them. It's just about the superposition method. So in order to verify the superposition, we are going to do a little bit simulation. So at some point, you can use different kind of softwares, LC Spice or maybe MATLAB, or there are different kind of softwares. But we are going to use some kind of simple and free software with the name of Falstat. I'm going to put the link on the comment for you, and you can just use it. At this point, we are going to prove that if I do have the circuit like this, for instance, if I would like to find the current that goes through here, the only thing I have to do is one time find the current or this middle current because of this guy, which is considered as I1, and the second time I have to find the current that because of this guy, which would be I2. And at the end, if I add I1 and I2, I still do have the same circuit. So I have to consider 3 circuits. One time with only V1, then with only V2, then with V1 plus V2, and finally I have to prove that the amount of current that goes this way is going to be as the same as the accumulation of all of these 2 currents, so don't worry about it. So the important part, finding the Thévenin equivalent. So we all know that what is the Thévenin and what is the Norton, but do we remember that how we could find that? So the main thing is that imagine I do have this circuit like this, and as you can see, I do have a voltage source, I do have the resistance, and I do have the 2K. At this point, it's not that kind of big deal. Obviously, you can do all of the calculation that you need, but imagine that the situation is going to be far worse than that. At this point, I'm looking for finding the Thévenin voltage. Thevenin voltage means that if I assume the parts that I'm looking through my circuit is A and B, and if these two guys are going to be considered something that we know as RL, what would happen to the voltage and what would happen to the resistance that guy can see throughout over here? In order to find a V Thevenin or V open circuit, the very first thing we have to do is we have to get rid of whatever load that we have over here, and we have to connect our voltmeter directly to this guy. So obviously we can do that very easily in practical section, but what about the part? The calculation part, if I make this guy as open circuit, it means that no current goes through that. So it means that that guy is just open circuit, nothing. So for finding the voltage that you could see through AB or these two terminals, the only thing that you have to do is find the voltage of R2. We know if we do have two resistance and if I do have one voltage source, I can either use the voltage divider or just simply find the current that goes through this branch or this through this mesh, and then try to find the voltage drop through the R2. So at this point we are going to use the easier way, because we know that V open circuit is going to be 15 multiplied by what? By 1.5k, which is going to be this resistance divided by accumulation of all of those resistance. And finally, we are going to have the voltage 10.77. So next part, we are going to show you that it doesn't, if we are going to use the simulation or practical, both of them are going to be the same itself. So for part 3b, we are going to measure the I short circuit, and we are going to see the R Thevenin and verify the model itself. What does that mean? It means that at some points it would be a little bit challenging for us to find a V Thevenin. On that point, we can find the I short circuit. Why I short circuit is good? Because as you can see over here, imagine we do have the same circuit and we would like to prove that the currents that we just found, and by the combination with R Thevenin is going to R Norton, is going to still give me the V Thevenin itself. So for this step, we are going to measure the short circuit current. What does that mean? It means that instead of just the load itself, as we used to have over here, imagine that it used to be like this. Obviously, we would like to see what would happen if we connect the whole circuit to RL. At this point, I'm going to get rid of that, and I'm going to replace it with what? I'm going to replace it with a short wire. Or at this point, we say that I'm going to replace it with a current meter. So current meter, because of the resistance is too low, we can consider it as a short circuit. So amount of current that goes this way can be defined very simple. Why is that? Because as you can see over here, right now, this resistance is getting out of the circuit. Why is that? Because this guy is a short circuit. And it means that my current prefers to move through this path rather than this path, because this path means that it has to tolerate more resistance, which it doesn't like. So at this point, my current is going to be what? Is going to be just simply voltage divided by the resistance. Is going to be what? Is going to be 7.5 milliamp. Let me use some kind of this kind. So I short circuit is going to be V open circuit, or we can call it as just a V source, and divided by what? Divided by R Thevenin itself. As you can see over here, you saw that my I short circuit was using another formula. That was the V open circuit. We just found it from the previous part, and divided by R Thevenin. What does it mean by R Thevenin? It means that by the way, R Thevenin and I Norton are the same, so you don't have to find both of them. Finding one of them would be enough. Finding the amount of resistance that you can see through A and B is simple. The only thing you have to do, you have to get rid of your sources. You have to make this guy as a short circuit, or if it was a current, you have to make it as open circuit. Then try to look at it. So let me redraw that. AB is going to be what? Contains two resistance, 511K. Then another resistor, 2K, is going to be in parallel with that. Why? Because you do have two common connection. Then you can find a combination of these two guys. You know, be 2K multiplied by 511K divided by 2K plus 511K. If you find that guy, it could be something around 1.5K. So 1.5K is going to be R Thevenin or R Norton. You can either find the I short circuit directly I'm using the ammeter. Or since you already have the V open circuit, you can find that and use the relationship, because as we all know, the relationship between the short circuit and open circuit current and open circuit voltage is going to be something like this. Either you can use that, or as we just saw, you can simply calculate it, right? If I consider this guy is going to be a short circuit, it means that my path will go through here. And if I assume that this voltage is there, it's going to be 15, it's going to be 2K, and it's going to be the current that moves this way. That's it. So the final step would be about the verification setup. So at this point, we are going to see that how we can some kind of show that everything that we had is going to be right. What we should do at this point, which is going to be about practical and simulation, we have to choose two different load resistors. At this point, for instance, we do have 10K and 1K. And for each load, measure the voltage across it when it's going to be connected to original circuit. Then measure the voltage across it when connected to your some kind of what physical Thevenin equivalent circuit. A voltage source set would be the V open circuit, and a resistance is going to be R Thevenin. The voltage should match closely. It means that it doesn't matter if you do have this guy as your main circuit, or this guy as your main circuit, or if you do have this guy as your main circuit. All the time, whenever you connect these three to the same, for example, load, you still have to have the same amount of current and voltage. So at this point, we were talking about different parts, and we were talking about the fact again, that what would happen if we are going to apply all of those components that we do have from the real world into our circuit, then try to calculate it and compare it with different kind of conditions. Condition means that when we are trying to find the current and voltage in three different kind of situations, calculation, simulation, and obviously practical, then we prove that the KVL and KCL works no matter what you're doing. All the time it works. You could have a little bit of difference between the numbers that you find. That is totally fine. And finally, we found out about the Thévenin and Norton. It means that it doesn't matter if I'm using the main circuit, if I go to the real one, or if I'm going to use the converted one. It means that Thévenin and Norton. At the end of the day, all of them would be the same. So I'm going to encourage you guys to completely watch these videos, because probably going to be in different chapters that we are going to have different kind of conditions, and it is going to be huge. So I'm not going to put it in one chapter for you guys. We're going to be so bored. Try to watch all of that. Try to do all of the calculation. I cannot do all of the calculation just for you, because we did it before, and this video is going to a lot of time. But try to do all of the calculation for yourself, then try to compare it with the simulation. So probably all of you do have access to equipments, but these two would be fine for you, because at the end of the day, the practical should follow this thing that we had before with a little bit of difference, because we know in our real world we are not going to have the ideal condition. We are going to have a little bit of errors, which were 4 errors. We talked about it. So if you guys enjoyed this video, I would be more than happy if you like it and share it with your other friends. Probably in the next part, I'm going to talk about other components, because so far I believe I covered everything. Yet, if you have any question related to that, you can comment me down below, and maybe I can make another video for that. I would be more than happy to do that one. But my name is Matt. Thanks for being here with me. Have yourself a great day, night, whatever. See you around.